So today we're going to be talking about the transitive property and substitution property. The transitive property is something that we've absolutely talked about before, and that's in 1.7 and 1.8 when we were dealing with the chain rule. So if we can remember from that, we're given that if A, then B, and if B, then C, by linking up these two conditional statements together, we can make the conclusion that if A, then C. This is called a transitive relationship. Yes, it's the chain rule, but it's also called a transitive relationship. And this is something that we can use in our proofs from now on. We're going to talk about some transitive relationships, some additional ones, and just to give you more of a concrete example of what a transitive relationship is. So we're just going to identify what are transitive relationships and what aren't, and a couple examples of that. So looking at greater than, this is going to be a transitive relationship. If we're looking at what's given to us in the beginning part of this example, if A is greater than B and B is greater than C, what can we conclude? So in this case, I'm just going to apply some numerical values to A, B, and C just so you can see that a transitive relationship is formed. So let's just say that A is 7 and B is 6, because this makes this first statement true, right? 7 is greater than 6. In this case, right, because we've identified B as 6, B has to be greater than C, or any value, let's say 5. Therefore, we can make that conclusion that 7 is greater than 5, right? If we're just applying that value, A is 7, C is 5. Okay, this, again, is true. So that's what makes a greater than relationship a transitive one. In terms of things that are not transitive, perpendicular to is not a transitive relationship. And that is based off of this example. So if line L is perpendicular to line M and line M is perpendicular to line P, let's see what type of conclusion that is formed. So if line L is perpendicular to M and M perpendicular to P, M is the line that we're comparing to both. So I'm going to first start by just drawing or writing out line M. Line L, right, we know we're given is perpendicular to M, which is in this diagram now. We also know that line M is perpendicular to P. So I'm going to show that relationship in this diagram. Now, can we make the conclusion that line L is perpendicular to P? Heck no. They do not look like they intersect at a right angle, right? They look like they are parallel. And later on we'll prove and see that they are parallel. But in this case, this is a false statement because they are not perpendicular. Supplementary to is another example in which this is not a transitive relationship. And you guys will be able to see this really, really clearly based off of our theorems that we've talked about before. So here we're given if A is sup to B and B is sup to C. Hold on, right? We have seen this before. It's familiar. We know that B, right, is the same angle. If two angles are sup to the same angle, then they're congruent. So we can make the conclusion that angle A is congruent to angle C, right? We cannot make the conclusion that A is sup to C. So that's what makes this statement false. The congruent to relationship, though, is something that is a transitive relationship, and this is something that we're going to use day in and day out in our proofs from now on. And I think you guys will really like it just because it's very, very concrete. So if we're given that about these two congruent segments, right, let's create a diagram just to put that visual and concrete example in your brains. So we know that AB is congruent to XY. Those two segments are congruent. We are also given that XY, segment XY, is congruent to segment CD. CD has one tick mark, XY has one tick mark, okay? Can we make the conclusion that AB is congruent to CD? Totally, right? They have the same tick mark, therefore they are true. This is something that we're going to be using in proofs a lot. So the theorem in proofs, what we will use is transitivity of congruence. The reasoning involves all statements. All congruent segments. And what I mean by this is if we're going to these if-then statements, so if two segments or angles are congruent to the same segment, then the segments or angles are congruent. If two segments or angles are congruent to congruent segments, then the segments or angles are congruent. So again, the only variation between these two are same and congruent. So this is more of like your chain rule, right? Connecting two or more congruent segments or angles together. The same is just like a two connection chain rule. The theorem for proofs, this deals with substitution. And when you're using substitution, you are using one equal or congruent statement and one other type of statement. Okay, so let's do an example of this. So these are the two things that you'll use in your proof. So substitution or transitivity of congruence. Those will be in your reason column. So if x is equal to y, then x can be replaced or substituted for y in any algebraic expression. So in our example, we know 1 is comp to 2 and 1 is congruent to 5. So we know, right, that 1 and 5 are congruent. Basically, they're interchangeable. So our conclusion could be that angle 5 is comp to angle 2, right? So we're just replacing 1, right, with 5. We're just substituting it because we have this congruent statement. And that reason would be substitution. Okay, we're going to do some example problems based on the given information. Some of them using substitution, some of them you're using transitive property, some of them you're using your other knowledge from geometry, right? Just pulling from that toolbox. So let's look at our first example. So we're going to state a valid conclusion and reason using all of the given information provided. So we know that CU is congruent to segment BS. RA is congruent to segment XY. Segment BS is congruent to segment RA. So I want to make some connections between these segments. Now I can create a diagram, but I'm going to create more of like this chain rule. So I know that CU is congruent to BS, right? I also know that BS is congruent to RA, so I'm just going to write that second. Okay, and then the third one, I know RA is congruent to XY. So because, right, I made those connections, right, between the congruent statements, I can say that segment CU is congruent to XY, segment XY. And that is going to be transitivity of congruence. In this case, it's angles. Or segments, sorry. In our other example for B, we're given angle 5 is sub to angle 6. Angle 1 is congruent to angle 6. So I know that 1 and 6 are the same measure, right? They're the same, they're interchangeable. dealing with the substitution property. I have 6 right in my supplementary statement. I know 6 is congruent to 1, so I can make the conclusion and just substitute in angle 1 for 6. And again, that's going to be substitution. Okay. For this next example, I know, and I'm given that ABC is comp to CBD. Angle EFG is comp to GFH. Okay, so none of these angles are repeating. The repeating angle is this guy. Angle A is congruent to angle, or ABC is congruent to angle EFG. Now, I'm starting to realize, like, hey, EFG, right, is the same as ABC. This looks super familiar to one of my previous theorems, right? We have two angles being complementary to two congruent angles. So I can make that conclusion that angle CBD is congruent to, angle CBD is congruent to angle GFH. And that reason is one of my previous reasons. If two angles are comp to congruent angles, then they are congruent. So it's not substitution, it's not transitive, right? We are just making that conclusion about our complementary statements. Okay. Let's talk about some proofs that we can create with this. And we'll probably have time for one. I'm going to try, or you're going to try the other one on your own and just pause the video after I'm done with this one. So we're first going to start by just writing out our given and mark up the diagram with that given information. So we know AE is congruent to EB. AE congruent to EB. We also know DE, segment DE, is congruent to segment EB. DE is congruent to segment EB. Now, I'm going to use one tick mark because I know that EB has that same measure as well, and that is given. Okay, so from that statement, I know that I can say quite a few different things, but what I want to get to is that E is the midpoint of AD. So if a point is a midpoint, then it divides that segment into two congruent segments. I'm thinking I'm going to need to use the converse of this because I have a point that's dividing, right, the segment into two congruent segments. Therefore, it's the midpoint because I know that conclusion needs to be that E is the midpoint of AD. Right now, right, in my proof, I do not have that AE is congruent to ED, but I can do it, or I can say that based off of the transitive or substitution property. And that reason, transitive, I'll say transitivity, sorry, of congruence. Now from there, I can go into saying that E is the midpoint of AD. That reason is if a point divides a segment into two congruent segs, then it is the midpoint. Okay, so I'd like you to actually pause this video, and then I will show you that solution after you've paused that video, or restart playing the video again.